Move on to the next talk by Professor Andoni Utsibera. He is the head of the Summer School of Myology, and many of us have attended these programs at the Institute of Myology in Salpeter, Paris, France. He is also the member of the executive committees of TREAT NMND Alliance and European Reference Network. He is a great friend of India. He has visited us many times. We look forward to your talk on NGS, New Generation Sequencing, and Neuromuscular Disorders, Good Clinical Practice. Professor Andoni Utsibera.
Okay, thank you for the introduction. Thanks to Shefali and to many other people. And I'm going to cover for the next 25 minutes or so the issue of NGS, which is next generation sequencing, and in the context of neuromuscular disorders. So these are my disclosures. It's true I work in different places, different institutions, and I have a pretty panoramic view of what's going on in neuromuscular diseases. So that's basically what we're going to talk about. Even NGS with the dummies, it means very simplistic things, but with also very interesting and exciting clinical applications, as we'll see, because this is a real revolution, as you will see. And then we'll address a very practical issue, which is how do we select a good laboratory, on which criteria, what should we order and prescribe for our neuromuscular patients. So just for those of you who are not very familiar with neuromuscular disorders, you should bear in mind that it's a huge and complex group of diseases. Okay, this is a rather conservative view of the problem, because I just put here the main neuromuscular disorders we know according to their location in the motor unit. That is the diseases from the hentoron cell, from the motor neuron, from the axon and the nerve itself, the neuromuscular junction, and obviously the muscle fiber. So altogether, with a very conservative view, it's approximately 300 to 400 different diseases. Okay, so that's complex, and for clinicians like you and me, it's pretty challenging. If you just take a less conservative view, then you will end up with more genes and more different entities, and that's what is shown in the gene table, which is published every year in the journal Neuromuscular Disorders, where our friends in Paris just list every single novel genes being published. And up to now, they reached the fabulous number of 800 different genes. But it's true that they include in this gene table disorders like cardiomyopathies, they include hereditary spastic paraplegia and hereditary ataxia. But still, the message is it's complex and it's highly variable, highly heterogeneous clinically and phenotypically. And that's another point I want to make. This is a cartoon where you can see different entities like Emery-Dreifuss, congenital muscular dystrophy, CMS, that is congenital myasthenic syndromes, limb-girdle muscular dystrophy, and there are some zones where there's overlap. Overlapping is there. And for clinicians it's confusing, and for geneticists it's also confusing. So you should keep in mind that some genes actually can give rise to different phenotypes, and sometimes quite distinct phenotypes, like distal versus proximal, something more central than peripheral, and so on. So, hopefully NGS occurred to be available since 2005, approximately. Remember, at the time, and we still have it, but at the time we had Sanger sequencing, which is sequencing, just one by one, nucleotide by nucleotide, spending a lot of money on that and taking ages to be performed. Hopefully, NGS is faster, it's more accurate, it's more sensitive, and nowadays it's even more inexpensive. So that's good news. And for all sorts of reasons, it has really revolutionized DNA sequencing. Remember, and I belong to a generation of myologists or specialists in these diseases where it took us ages, to clone a gene, to identify a gene, or to find mutations. Nowadays, it's just a piece of cake. You just get, a few minutes and you can just sequence everything and got a result and the answer for your patients. So first genome was cloned years ago. It took us a long time in different genome centers. It cost a fortune, approximately $300 billion. But nowadays you can sequence your own genome for nothing, or almost nothing. That is $1,000. And obviously, this is just a precursor of what's going on now, which is the personalized medicine, as we call it. It means that based on your genome, we can sort of infer your profile, and we can give specific drugs, and so on, and we can work on rare diseases in yourself or in other family members. So, this is NGS. I'm not going to tell you how it works. You don't need to know what's inside the engine of a car to understand why it works, but it works. The message I have for you is that sequencing is just part of it. In other words, the sequencing phase will take you less and less time now, but it's difficult is the data analysis. That is, analyzing all this variance, all this different changes in nucleotides that you will obviously find if you sequence the whole genome. So this is a process which takes time, actually, and that's why the turnaround time is not 1 or 2 days, unfortunately, but it may last for perhaps 3 weeks, 6 weeks, depending on the difficulty you're facing in your case. So that's how it works. So basically, people what are they doing in the lab? Actually, they're sequencing the genome, either extensively or just locally, and they're just analyzing letters, ATGC, how it's located, and they will compare these different letters to other genomes that they have in bank. Okay, that's as simple as that, I would say. But it takes time, and you can't do it manually or visually. You need to make it with a computer, a huge computer, a very powerful computer, just to compare the different sequences you've been producing. Just one word of caution, or just to be more explicit. Very often you're asked, or you ask the lab, what's your quality control? I mean, what's your criteria for being a good lab? And they will tell you, oh well, we have a coverage, we have having a very good depth in our readings of the sequence. And it's true that you need to know that some exons, for instance, just an example here, some exons are either fully covered, and you're happy because you're not going to miss any mutations in the particular exon, and other exons, like for instance exon 2 in this cartoon, which is partially covered. It means that half of it is not very well defined, and therefore you are going to miss, or you may miss, mutations in that particular region. So that's why you need to know what's the coverage, and as well what's the depth. Depth means that they will read several times the same region, and obviously if you read it many times, then the risk of errors is minimal. Okay, whereas if you just read it 10 times, 15 times, it's probably not enough. Okay, so you have the two parameters to consider when you analyze yourself the report that you will receive. Okay, so with that you can sort of detect all sorts of mutations. I'm just going to show you a few examples. This is a mutation found in a gene called BEAN1, which is responsible for centronucleomyopathy. Okay, you found it. It's a homozygous mutation. You have the diagnosis, full stop. You can even detect some more subtle changes, for instance, the small insertions and small deletions. I'm not talking about Duchenne, we'll come back to that later, but even the small stretches of nucleotides which are missing, then with the NGS you'll be able to pick them up. So that's good news too. And that was for this particular child with the MTM1 mutation, or a gene, which is a gene for myotubular myopathy, which is a congenital myopathy. Again, the sequencing is something, but it's not that long. What's very long is to analyze data. And the sequencer will provide you with a huge amount of data. Okay, you can put that either on a pen drive or a big mass storage, but still, you will generate a lot of data. Okay, and you can even retrieve this data for yourself. If you're addicted to NGS, you could even review the NGS data yourself in your room in the night, looking at it, but you won't be very successful because you need algorithm, you need all sorts of things to screen what you've been finding. Just one word about a FASTQ file, which is a FASTQ. Well, FASTQ is produced and generated by the sequencer, and this you can ask for it at the lab. If you're not happy with the lab, they should, in theory, provide you with this FASTQ file information, and you can reanalyze it later on with another lab if you wish. Okay, so a lot of bioinformatics. That's the point. And we're missing bioinformaticians everywhere. There's a bottleneck there. We haven't trained anyone, well, not enough people in that, but that's the bottleneck. Another bottleneck is this. When you screen the genome, even if it's the clinical exome or the exome itself, which is the coding sequences, you will end up with many, many variants. And what you have to do in the lab is to filter all these variants. Some are relevant, others are not. And the game is to end up with the minimal number of variants. Those who are really at the bottom here on this cartoon, and those 10 variants, for instance, those are the ones that you are going to consider, that you are going to study more extensively. You are going to search the literature, you're going to search the databases to know whether they are relevant to your patients. Okay? That's how it works. And you have all sorts of databases. Some are private, it means marketed. Others are just online, open source. And you have to compare what you've found in your patient with all that has been produced in these databases. Be careful. Those databases don't say always the same thing. There are discrepancies between these different databases. Be careful. About the variants, you have to sort of rank the variants. Some are clearly pathogenic. They've been described in other patients. There's no doubt. Okay, this is type 1. And then type 2, well, might be pathogenic, but we're not sure. And so on and on. And at the end of the list, there you have what we call the VUS, variant of uncertain significance. VUS, what's a VUS? Well, we don't know. It's a change, it's a nucleotide change, but it might have been described, but we don't know. There's no really any disease related to it, and it's very often lost. The point is that those large genes we know, like the Nebelin gene, or the Titin gene, or the collagen 6, all this huge gene, they generate a lot of variants, especially VUS. And therefore, once you see these variants from these different genes, say, well, might be true, but might be untrue. Okay, so you have to be careful. But also smaller ones, not the biggest ones, but small ones can also produce, and this is the top list. In my experience, with the CNO2 and thalamin C are also generating a lot of VUS. And forget about the technology. I'll be extremely brief about that. These are the different machines, the different sequences that were available not long ago. But all sorts of different equipment, very sophisticated, very expensive equipment, by the way. But in real life, actually, the winner is Illumina, because Illumina is almost a monopoly worldwide. See, they have extensive machines capable of processing huge amounts of data, huge amount of samples at the same time. So that's real life. You have to cope with that. It's very expensive still. Most labs now use Illumina. The point is that even if the equipment is expensive, the cost per genome is hopefully coming down every month, I would say. So that's been shown very clearly over the years. So it's cheaper and cheaper. Remember, the cost of sequencing itself, which is in blue here, in the blue bar, will probably decrease over time. It means what's going to cost a lot is not the sequencing itself, but the data analysis. the people that you were going to hire to interpret the data, yes, that would be very costly. So that's how it is predicted. But we know from an economic viewpoint that all this is profitable for the community. This is a very recent work done in Australia, where they applied NGS for all the unsolved neuromuscular patients they had, and obviously they turned out to be more profitable than having a muscle biopsy or having a sophisticated muscle imaging perhaps or something like that. So yes, it's profitable, and it's probably the way we're going to investigate most neuromuscular patients in the future. We have to compete when we deal with NGS with other people interested in NGS. Okay, rare diseases is just one field, but we have to compete, for instance, with people interested in cancer genetics, because they all do NGS. We have to deal with people interested in population genetics and so on. I'm saying that because in France, for instance, we have the same facility, we have the same core platform, and we have to, let's say, struggle a little bit with our colleagues to get access to the platform. Remember, there are a lot of collateral, what I call benefit, by sequencing so many people, not only patients, but ordinary people from different ethnicities, from different people, from different parts of the world. You will accumulate a lot of data about, yes, the history of the genome, the fabulous road of life, and this type of thing. So that's very promising. That's what they're doing, for instance, in Asia. They want to collect 100,000 people to sequence them all and to see and establish the different variants. It's important to know that all the databases we had to interpret the data so far were based on population from the West, America, Europe, but not much from Asia, Japan, and so on. So we really need this type of information to know whether a specific variant is really pathogenic here and not pathogenic there. That's key. Okay, and that way, if you're interested in population genetics, thanks to this work done currently, you may be able to trace the people where they've been migrated from Africa back to India and so on and on. That's fascinating. That's great. Now, for the clinician, what are you going to prescribe? What are you going to order? And there you've got a constellation of different analysis, okay? From the very simple ones to the very sophisticated ones. I'm not going to list all of them, but you obviously know that there are panels, which are limited studies for a couple of genes, sometimes 5 genes, 10 genes, 100, depends. They're usually disease-targeted. For instance, you have a panel for CMT, you have a panel for limb-girdle muscular dystrophy, another one for CMS and on. But obviously, what's perhaps better is the clinical exome. It's about 3,000 genes, and even more sophisticated is whole exome sequencing and perhaps whole genome sequencing and so on. But the more you get it wide, the more you get into trouble regarding data analysis, because you've got to have a huge amount of data, a huge amount of VUS, and you, at the end of the day, you might be lost. For those of you who are involved in neuromuscular diseases, obviously it's very useful, but for some diseases, okay? I listed them here. Limb-girdle, yes. Congenital muscular dystrophies, yes, and so on. For others, it's still debated. For instance, Duchenne muscular dystrophy, do you need the NGS study? Well, start with MLPA first. It's cheaper, at the same turnaround time, and you get the answer in most, well, it's 70% of cases. So you're happy. No need to go for NGS. But if you're having an MLPA negative Duchenne, yes, you have to sequence with the NGS. And we have at least 3 situations in which NGS is not appropriate. You're going to end up with a lot of mistakes or misdiagnoses. That is, for instance, spinal muscular atrophy that we've been talking about. Yes, that's an issue. Not much for type 1 and type 2, because clinically you can't miss them. But for type 3, yes. Sometimes they present like limb-girdle muscular dystrophy with proximal weakness. You think of limb-girdle muscular dystrophy, but you sometimes forget to think of spinal muscular atrophy. And With NGS, you will not pick up the delusion we've been talking about. Okay? So be careful. If it's facioscapulohumeral muscular dystrophy, same story. Okay? You won't pick it up by NGS. You need a specific test, which is very, very difficult and challenging, but you need a specific test. And same for myotonic dystrophy. If you have a big expansion, triplet expansion, yes, you will miss it with NGS. So be careful. So it's a wonderful tool in general, but for specific diseases you have to be cautious. Okay, what about, or why should we order the test? Okay, you have MedGenome in India, which is good to know. You have Eurofins as well, but MedGenome is really Indian, as far as I know. Eurofins is French, but this one is really Indian. They have been accredited just last year, December 2017, and CAP is real label for quality control. Okay, that's good news. That's good. So if you just browse their catalog, they have a huge catalog. All this is well organized. You can have information about the turnaround time, about the type of analysis they're doing, NGS or MLPA. They may have a gene list. For instance, this is a gene list for CMT genes. You can just screen and be sure that they have been doing it. So that's very transparent. Okay? What is not transparent actually is pricing. Because they always say book now. It means that you need to phone or you need to get in touch with them to know what's the exact price. Okay? Eurofins does the same as far as I know. I couldn't get to the website, the Indian website yesterday, but that's what we're doing in Europe, and we have the same kind of offer. Okay? Clinical exome, you can do it for a solo. Solo means just one individual. For a trio, that means individual plus the two parents, which is more powerful, and so on. It costs a lot still, at least in our country. This is another example that's in Taiwan. That's a panel of gene, a neuromuscular panel of gene, containing, I think, 236 different genes related to neuromuscular disorders. Now, how are you going to select the best lab? First of all, what I call notoriety, reputation. Okay, you have MedGenome, you have Eurofins, and you have others. Centogene, Invitae, Genomed. They all use the same machines. They all use the same databases. Perhaps some of them are better than others. I don't know, but certainly some are cheaper than others. Take into consideration the fact that they're also low-cost companies. Sometimes coming from China, South Korea. They just do it for 200 or 300 euros. Is it good quality? I don't know. Are they CAP certified? I don't know. So be careful with that. Of course, you will take into account the gene lists. Are they covering the newest genes? Yes or no? The turnaround time matters? Yes. I talked to you about depth and coverage? Yes. The type of samples, actually, most of them require blood samples. If you were lost in the middle of nowhere, in a desert or in Kashmir or I don't know, Himalaya, and then you need blood, okay? You can't really rely on DBS, even though some claim to perform it. Okay, so that's the type of report that you get. So I like the reports when it's detailed. You have information about turnaround time, about the genes that have been studied, about this and that. It's interesting to know whether there are a clinician. Sometimes there is a clinician in the team, in the lab, which is good news. Sometimes a medical geneticist. But there are limitations, as I told you. We're producing a lot of data, probably too many data. The diagnostic yield is not 100%. The best ones are achieving 50% in best hands. It's not enough for clinical practice. It's true that this yield is higher when you target your NGS, and it's much lower when you're having something like genome sequencing. And the other point is phenotyping. When you have a good clinician whose input has been very critical, yes, you're likely to raise your yield. Safety of data, yes, it's an issue. How we're going to store all this data and confidentiality is also an issue. So I will not cover the different success stories we've seen for the past 10 years or so, but believe me, some of our patients which were undiagnosed for 15, 20 years, all of a sudden, thanks to NGS, we made it, okay? And sometimes this was quite unexpected genes. I remember we had someone with arthrokyphosis and high CK, and we thought about congenital muscular dystrophy, and it turned out to be a congenital myasthenic syndrome with a presynaptic mutation in the FAMP1 gene. That's just one example among many others. Okay? So I already talked to you about the failures, that is the cases where you will miss this different alternative diagnosis. The final word is about dermatomyositis. What is that? Well, I remember that someone prescribed NGS in a typical case of profound muscle weakness, high CK, rash, but he didn't know about dermatomyositis. He thought it was an hereditary disease, and obviously NGS was normal. And when we performed the muscle biopsy, yes, we found the perivascular infiltrate. So be careful with that. Okay, that's another example. This is about neuromuscular dystrophy. So some of you in India are now doing NGS either on a routine basis or just as a research study. This is a paper which has just been released this month from Vellore, where they just screened a couple of patients with CMS, congenital myasthenic syndrome, using, I think it's an in-house study, and they reached the 70% yield just by screening 5 genes only, which was great news. Okay, this is what they obtained. So they still have this negative portion, which may be due to other genes, because they haven't covered, obviously, the 22 or 24 different CNS genes we know. So the final slides. What happens if your NGS studies is negative, unconclusive? What are you going to do? Then, and it's a key message, you have to reassess the patient clinically. That's key. You need to re-examine the patient. Is it proximal? Is it distal? Is it blah, blah, blah? Okay, you need to do that. Perhaps you'll have to do a muscle biopsy in that case. Perhaps another EMG. Perhaps muscle imaging and so on. You'll have to discuss the case with other experts, either locally or nationwide or internationally. We do that every day. You'll probably have to study the segregation of the data or the variants that you obviously found in the family to know whether they are pathogenic or not. And then come a lot of dilemmas. Should we do it again in the same lab? Not sure. Should we do it again in another lab? Then we will have probably to retrieve the FASTQ. Yeah. Or should we embark on a much broader studies like whole exome or clinical exome and so on. And as you may know, we have some initiatives in Europe, more specifically, where we restudy those unsolved cases. This is the Solve RD project we have now. Okay, so I will skip that. Cost, yes. Who pays? In my country, we have national insurance system, so it's covered. In other countries, it's covered by private insurances, but you have a risk of stigmatization, and they may revise your premium, which is not good news for you if you're a parent. The farmers sometimes covers partly this cost. For instance, Sanofi covers for Pompe panels, PTC, which is here, covers for MLP negative DMD cases, and so on. So, just one final word about India. I'm not Indian, but I love India, that's true. I know the situation, more or less. So you have all this, you know all this. But regarding NGS, the point is that because you have limited access to muscle biopsies and expert centers for that, and you obviously have to rely on NGS because it's available, it's still expensive, but more people have access to it now. So I think, in my view, it's an ideal opportunity for India to diagnose more and more patients. And it's coming. We've seen that in Bangalore as well, with a CMS study recently. And it's from a business point of view, it's a very good news for India because you've got all these bioinformaticians I was talking about. They're based in Bangalore. I mean, most of them are there, okay? And some of them are exported to the West, I can tell you. So, that's it. It's an ongoing revolution, a fantastic opportunity for emerging countries. It's a chance to identify treatable neuromuscular, and I'll come back to it in the second talk. But data analysis is by no means simple, and the clinical input is essential to interpret results. Okay, I haven't time to raise the ethical issues, but there are many. But still, it's a fantastic news for us and for our patients. Thank you, Daniva.
Thank you, Professor Andoni, to making our knowledge abreast. In India, already there are few centers who started doing, but we need to catch up a lot more. Any comments or questions? One or two? Those who are doing the work or interested?
They are.
Yeah, Ratnapuri.
I have one. Okay. I noted one in your miss in NGS was Pompeii.
Yes.
What was the reason for that?
The reason for that is the following. When we asked people who were doing limb-girdle muscular dystrophy panels, we asked them, did you put the GA gene in your panel? They say, what's the point? And we told them, no, because Pompeii disease can mimic limb-girdle muscular dystrophy. That's why. So I think by now they have revised the panel, because a panel is not something rigid, something. It's a moving target, so they can incorporate new genes. No problem.
When would you choose exome sequencing versus genome sequencing? Would you indicate that, or how would
Yes,
you?
you have to, because
how would you go about? How would you decide?
For me, at this point, and given the level of sophistication, I would probably go for whole exome sequencing first. I would not jump right into whole genome. Whole genome, we still have a lot to learn from the different variants, from the intronic variants. So let's start little with the exome sequencing.
Andoni, I'm Dr. Verma,
Sorry.
your old friend.
Yeah.
What is the results of the panels that you do? In how many you get a positive result?
Hello. We have the same yields. It's about 50%. Some of the panels are higher because the phenotypic selection is much stringent.
What do you do with the other 50%? Do you go to exome?
The clinical exome, for instance, in France, we're facing a bottleneck because I had a slide down there, but France is very socialized in the sense that we have centers, but it's all run by government. The private sector is almost absent. Okay, so we therefore have to rely on those genome centers. We have to wait. The turnaround time for a clinical exome is about 3 to 4 months at least. So we're not as good as yours.
Thank you.